Going to be at the very end. I expect most of the talk should be accessible, so please stop me and feel free to interrupt. I would appreciate that. I'm going to start with a claim, which is not very controversial, but I'll justify it in two stages. Graphs are analogues of Riemann surfaces. So by graph, I'll be a little bit more precise what I mean by a graph, but I'm thinking of something like one-dimensional CDW complex-ish. I'm not going to really use the definition of Riemann surface. Think about pretzels, but they're not topological only. They have complex structures, and they're more rich than just a donut. Okay, so let me give you some first approximation of why this claim is not outrageous. I'll come back to it in a more sophisticated way soon. This has been known to geometric group theorists for quite some time. For example, they study the moduli space, or the space of all possible graphs, in order to understand certain groups, other automorphisms of free groups. The action on that group, on that big space, is studied via this geometric object, the same way that the action of mapping class group is studied by studying Teichner spaces. So this is one existing connection. More down to earth in probability theory, and especially the theory of random walks, people would like to know certain Green's functions, and sometimes they're very difficult to compute. But what they do, actually, they pretend these lines are actually tubes, so they thicken it a little bit. And in fact, if you do that, you immediately see that this and this are really the same pictures. If you put tubes here instead of lines. And then you get some idea, because complex geometry and complex techniques are very powerful, and people have studied them for a long time. You get some idea what the Green's function should be, and in some cases you take that idea and then you actually do it by hand. So this was a technique that has been known, maybe more related to my talk, at least morally, is the newer notion of something called tropical algebraic geometry. There is a notion of, so classically, on Riemann surfaces, people did study something called divisors, always Jacobian map, Riemann rock theorems, and things like that. Fast forward to 21st century, these things have been now introduced for graphs as well. So this analogy, at least at the level of analogy, exists. And I'll be a little bit more precise, both about the analogy and some of the words that I'm saying in the last item soon. But let me, so this is a claim, I'll come back to it. Let me go and do some specific definitions and quantities that I want to attach to graphs. So first of all, what do I mean by graph? I mean, a metric graph is what I really care about. A metric graph is a compact, so it's a finite thing, connected topological graph. When I say topological graph, it's geometric realization of a one-dimensional CW complex. And then I endow this with a metric. It's a metric space, but it's an inner metric. So everybody hopefully knows what metric is. But inner metric is a metric such that the distance between 2 points is equal to the length of the shortest path between those two. So you can imagine, you can give a definition of length or path, and then you can measure the distance, and that distance should have an inequality with a metric. And I'm insisting that it will be the sort of shortest path metric. I hope, I don't want to be too pedantic, but I hope you can imagine something like this is precisely giving me a metric graph in my definition. It's compact, it's not some infinite graph. And I've told you essentially if you want to go from the top point to bottom point, the shortest path is 1. But this 4 is like if you insist that you want to go via this path, so that's not the metric, but if you maybe pick 2 points on this right-hand edge, and you want to go, you can say proportionally how far they are by looking at the number 4. And maybe divide. You go 1/3 of that, maybe 1/3 of 4 is what you're doing. Of course, this is not the usual notion of graph when you think about graph. The usual notion, if I want to give this data to a computer and do some computation, I probably will pick a bunch of points and call them vertices. I will be forced to pick the top point and bottom point for sure. But then other than that, I have some choices. Do I want to pick vertex here or there? And I decided to pick a vertex to the middle left, middle right, and then top and bottom, and then so Sorry, I rotated this 90 degrees. But I'm giving the same information in a combinatorial way so that computer knows what object I'm talking about. There's a conceptual difference between the two pictures. When you do combinatorial graphs, you kind of insist that these are the accessible points. The dots are the ones that you are allowed to touch. And these are relations. They are saying that the top vertex and the left vertex are related. There's an edge between them. But in the first item, I want every point to be touched. Every point is created equal. Here, there are some distinguished points. Okay, but anyway, this is hopefully clear that it carries the same amount of information if I want to record it. But much older than all of this is the notion of electrical networks, which is my undergraduate degree. People like Kirchhoff already in the 1800s, and in fact not for applications, they were mathematicians. They wanted to study something called electrical networks. They had this concept of resistances. And the length 2 should be thought of as 2 ohms, maybe, two units of resistance. And if you want to think of this picture as an electrical network, you can think of these lines to be created from the copper wire, and the longer the wire is, the more resistance you have if you want to send electric current from that path, right? So it gets more warm if you put a battery across it. And these wiggly lines are the typical way of saying what electrical networks are, electrical resistances are. So I'll switch between these points of view, and I will put them in a very fancy looking context, but any questions about what graphs or electrical networks are for this talk? What I want, the main object is this top one, but it's often useful for computations to think about other points of view. Okay, so as an electrical network, you can define a function which is very natural from physical intuition, and you don't really need to be an engineer or even a mathematician to appreciate that. People buy batteries and they want to run small motors, and there's some potential function which is the key to solving many electrical network problems. So you go buy a battery, which unfortunately is very expensive. This is not a typical battery in grocery store. You get a current source, not voltage source. When you buy a battery, it fixes the voltage across the top and bottom. But this is a multi-$100 battery, which fixes 1 amps of current between the. So this is the current source. I connect it to a point. This cloud is some kind of electrical network or metric graph. I connect this battery across Z and Y, and then I go around and compute the potential difference between X for various X's and Z. So in other words, I'm thinking of Z being the zero potential. Potential is well defined up to a constant, so another way is to think of always potential differences. So in this way, I get a function in 3 variables. Y and Z were my endpoints of the battery connected, and X is the one that I'm computing the potential at. This is a obviously very important function. It's the key to solving electrical network problems. It's a potential function. It's potential, well, I can say in many words, fancy words, but this is the key to solving the Poisson equation in particular. And from this, you can also define something called effective resistance between 2 points. So I hope you know enough of Kirchhoff's theory that you know voltage is resistance times current. And you should know this even if you've never took a course, because sometimes you buy a device that has an amp rating or watts rating and you want to compare them, you better know that your basic physics. So if I put a current 1, then if I is 1, R is V. So the potential difference is precisely the effective resistance. And in this picture, what I'm going to do is I'm going to say X is equal to Y. I'm going to look at the potential difference at Y and Z. Then the resistance is precisely what I'm measuring. So resistance between X and Z is the diagonal of that J function. Is that clear? So I'm putting my probe exactly at Y, this X is here. And this is the key to some of the formulas I'm going to say. And again, it's the same kind of thing. Maybe you have seen the parallel law that you can, if you have x and y, the effective resistance between x and y is 1 divided by, let's say this was 4, 1, and 4. Probably remember the parallel law. That's the kind of thing that you can compute. But I'm saying you're allowed to touch every point in the network. So you have a function in 3 variable on the entire metric graph. So it's a function from gamma times gamma times gamma to real numbers. You can put your probe anywhere you want. When you do this kind of things, you're constraining that these are only accessible points. What do I want to do? So everything I've said so far is like 1850. Now, what I'm about to say could have happened in 1850s, but it's actually some construction that came up from arithmetic geometry all of a sudden. It's still electrical networks. I'm not going to use any other. But these names are arithmetic geometers. Ted Chinberg, I think he's still active in University of Pennsylvania. I didn't check his website. Romley retired recently at UGA, and Shobu Zhang, Princeton professor. Around 1993, even though privately these things existed a little bit before that, proved the following weird statement. You write a double integral. I just defined effective resistance. And you compute against a measure. So for any measure of total mass 1, and I'm not saying probability measure, I'm allowing negative numbers. You can write a double integral like this. And I'll justify it in a moment from physical intuition why you would write such a thing. And then they prove that there is a unique measure that makes this double integral maximal, maximizing this integral. And this is a key definition for my talk. Before going further, let me say what kind of thing I'm talking about. Forget about graphs. Just buy a piece of metal. Think of it like a metal in complex numbers, and then put some electric charge on it. I hope you know electric charges that are of the same sign don't like each other, they want to repel, they want to go away. So if you wait a little bit, they will move to boundary because they want to maximize their mutual distances. The total mutual distances should be maximized. That's something that physicists can make it precise, but intuitively, they want to go away from each other in a way that the total distances is maximized. I have a notion of this effective resistance, which you can prove it's a distance function, in fact, but don't worry about it. And I'm saying that there is some configuration, it's like this yellow configuration on the graph that maximizes the total sum of mutual distances. Okay? And in fact, you might want to think of this yellow configuration as equilibrium. When things settle down, what happens? You might want to call the maximizing configuration also equilibrium measure. Okay? And in fact, in this situation, you can give a measure of complexity of a region, called it capacity. So it's different from its size and Lebesgue measure. It's a more so-called potential theoretic measure of complexity of a region in the complex number, and that maximizing quantity, you might want to think of it as capacity of the graph. So these are sort of by analogy, you can do these things. But anyway, some number theories for some reason were doing these things, and in fact, they also computed what this measure is. I'm not going to use this computation, just I wanted to make it clear that there is a continuous part for this measure, and there is some discrete part for this measure, and these are interesting and important, but maybe it's just an excuse for me to tell you the continuous part has some quantity on edges, which is 1 minus effective resistance across that edge. I have already said what effective resistance is, divided by length of that edge. And this has connections to probability theory as well. It's something about random span trees, but let's move on. I'm not going to use this formula, just this equilibrium measure can be computed, very explicit, it's really cool. what I do care about is actually the maximizing quantity. Was there a question? And that's what is called tau constant. This was studied by Romney. It's the corresponding capacity, the maximum that I was talking about. When things settle, what's the biggest number you can get from that double integral? And in fact, it can be computed using effective resistances. There is some formula. It's mysterious what this number is, the way that I presented it. There is some integral formula for it, which was worked out. It can be described as some Dirichlet pairing, but it's not very computable, and maybe let me just reassure you this can be computed really, really quickly, and I will come back to it later. So the way that you compute it, again, I don't really care about the actual formula, but these are some effective resistances that you can compute. I told you, if I give you a concrete problem, you can compute effective resistances. There are linear algebraic ways to do these computations really quickly, and this f of e was this formula in the previous slide. Again, was some effective resistance computation. The message from this box is that you can compute this. And this was implicitly done in a PhD thesis by Shinkev Zubair, which was a student of Romney, and the way that I've described it here was something that I did with my colleague Robin de Jong at Leiden University. And let me just say one more fact before moving on to a seemingly different subject, going out of electrical network. Romney, in a private letter in 2000, I think early 2000s, but it's a private letter, I don't have it. He writes to Zhang that this tau is actually less than or equal to quarter total length of the graph, and the equality holds if and only if the graph is contractible. It's a tree. Okay? So I'll come back to this later.
The length of the graph is sum of the edge lengths?
Exactly. So 4 plus 1 plus 1. Total volume of the graph. Any other questions? Again, don't worry about the exact formulas in boxes. Just general idea is that this is computable, maybe the main message of this slide.
Is there like a meaning for where sort of the 1/4 comes from?
So 1/4 is 3 times 1/12, and 12 eventually, in a fast-forward way, is a Riemann rock number. But I'm not going to talk about those things. You'll see a lot of multiples of 1/12. This is related to, so maybe you don't know what Riemann rock is, but many people know Pick's formula for computing volume of a polygon by counting number of lattice points. There's also a 12 there. And it turns out Pick's formula can also be proved using what I call Riemann rock authoric variety. So 12 is a Riemann rock number. Whenever you see it, you should be suspicious. Some algebraic geometry is behind it. But I mean, this is a concrete computation. You never need anything fancy to. All right, so I'm going to go up to now with doing electrical networks, and I will come back and justify why electrical networks and number theorists are friends. I'm going to talk about geometry of graphs in a way that is much more modern. So I'm going to define, I said graphs are like Riemann surfaces. You don't need the next sentence, but it was known to Riemann and Jacobian and others that Riemann surfaces have some really beautiful object, which is abelian variety attached to them. It's some kind of a linear algebraic object that knows a lot about the Riemann surface itself. You don't need to know the details of this. Concretely for graphs, I'm going to do that. So if graphs are like Riemann surfaces, do they have this object that I'm talking about? And the answer is yes. Any graph of genus G, where G is some concrete number, pick a vertex set, and then count your number of edges minus number of vertices plus 1. So you can think of it as like rank of the fundamental polygon. Has a real torus attached to it, which I'm going to describe right now, of dimension G. You start with the first homology of the graph, but concretely this means you look at the integer value to close. So my running example was this. There are some metrics on it. For now, I'm just gonna forget it. And I'm going to describe a flow, it's good to put some arrows on your edges. And a flow is something that is kind of conservative at every point. You don't have excess and shortage at any point. So let me concretely, think of like water passing through this pipe at this rate 2, and then -1, -1. So at any point here, 2 units of water is coming in and 2 units is going out. At this point, 2 is coming in, -1 is coming in, which means 1 is going up and -1 is coming in. So 2 units comes here and then 1 unit goes there, 1 unit goes there. And the same thing for the top one. It's some kind of a circulation of some physical thing in the graph. It's a flow. But I'm insisting, so this is one very concrete way of saying what's an element of the first homology of the graph. If you know topology enough, you don't have to listen to the nonsense I'm talking about. But it's very concrete. And I'm insisting it's integer valued. So for some reason I'm insisting that you are not allowed to put pi and r and e and things like that. And you can immediately think of this as some kind of a group, because if you have 2 such things, you can add them. There's a zero flow with some group. And in fact, it's kind of weird that I'm insisting it should be integer valued, so let's go ahead and think about the real valued version of this as well. So I'm going to make a vector space of real valued flows, which now an element can be, I don't know, pi plus e minus pi. The advantage being now I have a vector space, I can scale this with a real number as well, and I still get a flow. So I have a subgroup of a vector space. And you can imagine what I'm going to do. I'm going to look at the quotient. I have a vector space, I have a subgroup, I look at the quotient group. Okay?
What's the group operation?
Just adding these things.
Oh, just adding.
If you have this and you have 3 minus 2 minus 1, you can add them and you get 5 minus 3, and please correct me if I'm too close to the board, minus 2. And the same scaling also is allowed, so you have a vector space. A vector space modulo a lattice is going to give you a torus, a real torus. And it's G-dimensional, where G is that number I was saying, number of vertices, edges minus number of vertices plus 1. That's an easy observation. But I don't want just a topological lattice. Notice that I forgot something, which I never used, the edge lengths. I want to somehow remember those edge lengths as well. I've been forgetting. Yes?
I was going to ask, from like a classical graph, we usually count, like, if you remember the one from a couple slides ago, you had the 4 vertices, and then 2, like an edge from, yeah, and this one exactly.
I guess that's called height graph in graph theory.
Yeah, so in this case we have, let's see, it's 1, 2, 3, 4,
So
5 edges.
Is going to be 2, is that what you're worried?
Well, I was just asking, like, how do we count edges and vertices in the, like, this more continuous graph?
Oh, good point. It's invariant. Just pick your model and compute number of edges minus number of vertices plus 1, and you will always get the same number.
Okay.
So if I want to add this and do that, the point is adding this is going to add 1 vertex and 1 edge.
Oh,
They
yeah.
cancel each other. It's
Okay.
related to the fact that Euler characteristic is a topological invariant,
Okay.
which means fixing your combinatorial structure is not going to change.
Thank you.
Other questions? Okay, so I was saying this thing is a torus, G-dimensional torus, but it has more information. I would like this word polarization. It's just a fancy way of saying I want to remember the edge lengths. I forgot them. I should be quicker in clicking. Is that the problem?
No.
So polarization is going to be some metric data that I want to add to it. I don't want it to just be a topological torus. I want to remember this data of what I call cycle intersection. So it turns out these flows have some basic flows. So some basic flows are these cycles. So if you pick a cycle in your graph, I'm going to forget the other edge. You can put 1 and minus 1. So you can go around the cycle and make a flow out of that. Just think about water just circling in that cycle. And the same thing for this 1 and minus 1. And it turns out the space of flows is generated by the space of cycles. So it's enough for me to tell you what is the pairing of two cycles. And I've given it away, cycle intersection pairing. So you look at the two cycles, you see where they intersect. In this case, if you want to compute the pairing between them, the intersection is going to be the length of this edge. The left edge is common between them. So it's going to be length of, let's call it E1, which was 4, I guess, in my E1 was the left in the first picture. Okay? So I remembered something about the length. So in fact, you should think of this not as a topological cycle. It's, in fancy terms, it's a topological torus. It's a topological torus plus a Riemannian structure on it. I'm telling you how to compute something in the tangent space. Let me do a very concrete, in fact, I have started doing this example, but let me do it like with a picture. The example I've been talking about. For now, I'm going to forget about, actually, let's assume all the edge lengths are 1, just because it's going to be easier for me to draw the picture without worrying about angles. Okay, so cycles in this graph are E1 minus E2, the left circulation, E1 minus E3, the big circle, and E2 minus E3. Well, it turns out if you add E1 minus E3 and E2 minus E3, you get E1 minus E3. So 2 of them are enough. It's a 2-dimensional torus that I want to draw. And then I've drawn a specific angle between them. Why is that? Because E1 minus E2 and E1 minus E3, if I pair them, I should have length of E1, which is 1. And then I hope you remember your cosine formula from linear algebra. Angle between two vectors is their dot product divided by the lengths. The lengths are going to be length of E1 minus E2 and E1 minus E3 is, each one of them is square root of 2. So cosine of theta is 1 divided by square root of 2 times square root of 2, 1/2, and cosine of theta 1/2 should give theta, I hope, 60 degrees. That's the 60-degree angle here. So some kind of a rigid torus that I'm drawing. And of course, I was looking at the vector space modulo the lattice. So it's the red parallelogram is a fundamental group, a fundamental domain for that torus. And I mod that out and I get some torus with the extra structure of this. In a way, I was telling you the Riemannian structure. You can think of the vector space as the universal cover, and I'm telling you. You have a question? There was one hand up that I was.
I did have this question about, do you always have to orient your flows the same direction?
No, but if you change, so this is just because I want to draw pictures. But if you flip, you get an isomorphic copy. So everything is up to isomorphism. I just want to draw pictures, so I will pick some orientation. This is something people do in topology. If you want to complete homology, first fix an orientation, and then you say, okay, everything I did up to isomorphism is independent of the choices I made. And show them. But the isomorphism are also easy to do. Other questions, comments? Okay, so this is, I think, for many of you, is some, even if you have seen graph theory, you haven't been playing with these tori attached to them. But it comes from the point of view that if graphs are like Riemann surfaces, there should be all these baggage that comes with Riemann surfaces, and I'm telling you this is the baggage Jacobi was interested in, hence the word Jacobian. For the Riemann surface case. This is fast forward 21st century version. And I will say fancy things about this later, but I hope this is down to earth enough that everybody follows. Okay. Now, in fact, let me go back. I'm going to, if it's okay, I'm going to erase the example. I'm going to record this lattice picture on my ongoing example. This was 0, some vector here, some vector here. Just remembering that picture. So I claim for lattices, there's a very natural function you can think of. And this also has motivation that is completely out of the subject can be completely out of the subject of my discussion, my presentation. Namely, think of the blackboard as like some continuous data that you have, and you want to quantize your data by restricting your output to be the lattice points. So you give me a point here. My computer wants to have some digital data, so I have to round it to the closest lattice point. Okay? And there's an error, and I want to remember this error. And that's what I'm doing in the first item here. You give me a point in the vector space, I'm going to find the closest lattice point, and I compute the distance according to I have a bilinear form, so I can talk about distance. Okay, distance squared. I'm remembering this number. Is that clear? If you are not a number theorist or algebraic geometer, the name I've picked for this is weird. What is this norm of theta? But it comes from some algebra geometric point of view for me. But this is kind of error for quantizers. I'm remembering the error for quantization of a given sample. Right? What you can immediately observe that this is periodic with respect to the lattice. Namely, if you go from here to a translate of that, this translates, then you get the same output, right? So it's invariant under translation, which means that it descends to the Jacobian that I defined. So it's actually a function on the torus. Right? It's a well-defined function on the torus because it's, when you quotient out by lambda, you get the same number. Okay, now you have a function on a torus. The torus comes with a natural Haar measure. I have a metric on my torus as well. So there is some general measure theory statement that maybe it's even covered in Jackson's class, that compact Hausdorff groups have some natural measure attached to them. And if you have a function and you have a measure, you definitely want to take the integral of the function against that measure. And that's what you compute, and I call this tropical moment or something. And there is a more down-to-earth version. If you know Voronoi polytopes, you can say what this is in terms of Voronoi theory. But let me skip that. Let me just say this is also a quantity that people that did quantization must have studied and have studied. Namely, this is the mean squared error for my quantizer. I have this function that for any input, you get an error, and I'm averaging out my error. I'm saying what's the typical, what's the expectation of that error. That's what I'm computing. And I'm going to, I guess I didn't write it, but the Haar measure is well defined up to scaling. I'm insisting that Haar measure of the Jacobian is 1. I have to normalize it one way, but it's pretty clear that there is one obvious choice, and I've done that. Otherwise, what I'm defining is well defined up to a constant, which doesn't make sense. It's just a quantity. Okay. That was what I was advertising. If you have a quantizer, it's just mean squared error. And as such, it must have been studied, and it turns out Conway and Sloan have a beautiful book on lattices and sphere packing and things like that. Their very last chapter is a horrendous set of computations on computing this number. Maybe their normalization is different from mine, but computing mean squared error of lattice quantizers for root lattices. And in each case, they work really hard, and they compute the mean squared error. It's expected that computing this, what I call tropical moment, is very difficult. In fact, people, and I believe them, when they say that this should be in computational complexity terms sharply hard to compute. So worse than NP hard. Conjecturally worse than NP hard. Okay? So far I've given you two numbers. One was tau coming from electrical networks, and one is I coming from first building this geometric torus, and then computing some, I hope I convinced you, natural looking state number. And result that we prove is that these two numbers are not actually that different. They have a linear relation between them, So the tau, the number theoretic invariant, plus I is the total volume, the sum 4 plus 1 plus 4, as I have mentioned before, up to some constants that are written explicitly. Okay? And I want to make some comments. First of all, if your graph is contractible, so first of all, I is bigger than or equal to 0. It's just computing some positive number, integral of some positive function. So it's bigger than or equal to 0. So you immediately get tau has some inequality with L, which sounds like something Romney had done in 1990s in a private letter. And in fact, this is precisely saying what the error term is, because when you have a contractible graph, you cannot possibly have any first homology, or in the language of flows, you cannot have any flows in your graph, which is non-zero. A tree does not have any circle in it to have a circulation flow. So this is 0 precisely when the graph is contractible. So I'm telling you, if it's not contractible, here is the error term. The proof that went into this is a very difficult computation that uses probability theory, convex geometry, electrical networks. Well, electrical network obviously should be there because tau is there. Convex geometry, well, I'm doing lattices. You can imagine I mentioned Voronoi polytope and things like that. And probability, I also mentioned this very quickly, this connection to random spanning trees. I glossed over it very fast. So it's a totally combinatorial proof. As a consequence, I mentioned I is difficult to compute in general, and for root lattices, they work really hard, and in general, people think it's sharply hard. But I did tell you tau has a very concrete formula which is very computable. So as a consequence, you get that I is also very computable. And I cared about this computation from number theory point of view. I'll get back to this. Romney's inequality is a consequence. But let me tell you, historically, actually, we were led to this by a work of a Colloquium geometer, a Ph.D. student of Faltings, which, under this analogy between Riemann surfaces and graph theory, he was actually doing something about Riemann surfaces, and then we kind of took that and said, what does it mean for graphs? What would it be the corresponding statement for graphs? So we wrote this down, we completed some examples, and it was correct. Then we had to only prove it. But the techniques were totally different, because here you have a Riemann surface, you have moduli of Riemann surfaces. He really used actually solving Poisson equations on the moduli space of Riemann surfaces. Those techniques just didn't exist here. So we had to do pedestrian way. There is ongoing work with Robert that we actually have a uniform proof of both of them using some fancy new technology, but that's not what I'm going to talk about. So soon there will be a paper that puts these theorems on equal footing, Archimedean and, okay, Archimedean, I mean the Riemann surface complex version, and non-Archimedean, I'm going to come back, why graphs are non-Archimedean. And our motivation comes from number theory, which I will get to at the end of my talk. Okay, I want to go back, now I want to sort of take this, so far everything was combinatorial. You could teach it in a presumably undergraduate class. But in order to import this technology and this computation to the realm of algebraic geometry and number theory, you need a more, not just a philosophical analogy, you need a tool that takes this and pulls it to algebra. I will try to convince you in a couple of slides that graphs are Riemann surfaces, not just are similar to Riemann surfaces. But you have to bear with me, what do I mean by that? So let's go back again to 18th, 19th century. If you have a variety over C, by that I mean just solutions of a bunch of equations. And in fact, already for this, it's good to think of solutions to, I'm going to have a running example, solutions to take the polynomial 0, but think of it as a polynomial, not just a number. And look at the solution to polynomial equation 0 is equal to 0. This is a bit of a, so f is 0. of course, f of z is 0, which means the solution is everything. Algebraic geometers use this notation. So this is going to be A1. The solution over complex numbers is going to be C. Okay? So this is my X in this slide. You look at the C points of your solution to your polynomial equation. But then algebraic geometry has this weird topology which says a set is closed if its solutions are yet more equations. So in this situation, a polynomial equation is just a polynomial in one variable. Solutions of a polynomial in one variable is just going to be a finite set of points. So a set is closed in this set if it's a finite set. In other words, opens are cofinite sets. So take your complex plane. An open set is going to be complement of finitely many points. Okay, that's not the topology you want to work with if you're teaching a complex analysis class, right? What you do, you change your point of view. You say, these complex numbers have absolute value. I'm going to define disks, like all the points that are of distance at most r from a given point. And that should be my open set, not this cofinite weird set. And then you do analysis with that. So if you want an analytic space, you change your Zariski topology, that cofinite set weird thing, and you use the analytic topology, the one that comes from absolute value. Okay, and that's so obvious that we don't even bother giving a 10-minute lecture at the beginning of complex analysis class. This is the right thing to do. That's the running example I had. You get a complex plane when you run this machine. And if you had a curve in algebraic geometry, if you had a bunch of equations that define some one-dimensional object, and you run this technology, you get Riemann surfaces, right? If you use something called abelian varieties, which I will come back to later, but it's Jacobians, which I was mentioning earlier, are very important examples of abelian varieties. You get complex tori. By complex tori, I mean some C to the G modulo some lattice inside it, which is full rank. This is a complex torus. What I'm saying is that if you start with something called abelian variety, including Jacobians, and you run this machine, you get an analytic object which is this way. It's C to the G modulo lattice. Okay? All right, so let's do the same thing for different fields. So why do I care about non-complex numbers? So first of all, if you're a number theorist, you might have heard of p-adic numbers, and this is important for my application. If you're a geometer, and in fact, already Newton was thinking about these kind of fields, like Laurent series in one variable. These are things that have infinite power series, but the infinite is only on one side. So there is an index at which power of t cannot go below. So for ai t to the i's, where I is at least I0. Already Newton cared about these things because you can have like a complex system which has a parameter in it, and you want to know what's the limit of that when the parameter changes. So these are, if you're a geometer or number theorist, but maybe if you're not convinced, these fields are everywhere. So there's a theorem that says if you think about fields with absolute values, you have a notion of distance, and it's in analysis, you want to know whether your space is complete in the sense that Cauchy sequences converge or not. Like Q is famously not complete, and you complete it and you get R. It turns out there is a theorem due to Gelfand and Mazur, not Barry Mazur, another Polish Mazur. And I should pronounce it more Polish, I don't know how to do that. That says the only complete Archimedean fields are the two examples that we know, R and C. By Archimedean, I mean the triangle inequality is the one that you know. This is a strong triangle inequality. The usual triangle inequality says x plus y should be less than or equal to absolute value of x plus absolute value of y. The only fields with that property are the two weirdos are R and C. Every other field, and there are infinitely many of them, in fact I've written infinitely many on my board, because for any p prime number, you have a QP. And there are many, many, many examples that go beyond this. All of them are non-Archimedean. So if you want to do analysis over arbitrary fields with absolute value, unless you're super lucky and hit these two weird fields, R and C, you're going to be hit with these fields, and you have to learn how to deal with it. Okay, as a pure mathematician. And you might be tempted to do exactly the same thing that I did. You start with your variety, you look at your k points, you use your, not the Zariski topology, but the topology that you can define disks using this absolute value that you have. And then here's the problem. No matter what field and what example you're working with, you're going to end up, you always end up with a totally disconnected space. You have been very lucky that real numbers, the moment you complete Q with usual absolute value, you get a space which is not totally disconnected. It was weird. In hindsight, this must not have happened. There is some very special pathological property of reals that makes this happen. Typically, this should not happen, and it does not happen. It always does not happen, almost always, except for R. So there is a completion of a different type that one should do. We call in the analysis class, we say we completed, but we kind of got lucky, we didn't really have to complete it. That worked. You were trying to fix the analysis question, the question of Cauchy sequences converge or not. You fix the topology with the same snap. That shouldn't have happened. And there are different solutions how to fix this. The one that I'm going to talk about and is very useful from my point of view is a solution due to Berkovich, which says essentially there is a very natural way to add points. This totally disconnected space misses some points, and there is a canonical way to add points and fix that. And the way it works is not very different from some ideas of, again, Gelfand in operator algebra, which I don't want to dwell on, but very quickly the idea is that you should look at the space of functions on this space and look at the characters on that space. That's been a very important idea historically in 20th century. Instead of going through the details of how this is done, let me draw some pictures, or show you some pictures drawn by other people. So think of the example up here, like complex numbers, but do it for a non-Archimedean field. Think of this totally disconnected set of points as the bottom of this tree. So these endpoints at the bottom. And the Berkovich's solution adds all these points above. It makes some kind of a space which is very connected. It's like a tree, looks like a tree, some hairy thing. And if this is your analog of complex plane, Riemann surfaces locally look like complex plane. It has a covering up by patches that looks like complex plane. Then you can guess what should be the curve over non-Archimedean fields. Locally should look like a tree. Well, if you zoom out, you might have a global topology, but locally, if you zoom in anywhere here, it looks like a tree. Now you can see that I promised that there is a way to think of graphs as Riemann surfaces. They are Riemann surfaces, except they are Berkovich analytic. Analytification over non-Archimedean fields. They are non-Archimedean Riemann surfaces. And they have this annoying hairy stuff attached to them. So what I was really concentrating was this core, this skeleton inside here. But it turns out these hairy stuff are not going to be a problem for my application. So there is a sense in which Berkovich analytic curves are precisely some tree plus hair. So let me quickly go through that. You have a non-Archimedean analytic curve is essentially just a graph. For any compact graph, you can actually build the Berkovich space that the graph is sitting there. And for abelian varieties, which I haven't defined, I don't intend to define, but maybe you have heard elliptic curves. I'll come back to that. These things are going to be a real torus plus some hair, but higher dimensional hair. Actually, I want to, it was hard for me to draw it on the slide, but I want you to have a picture like this in mind. So you have a real torus, maybe in this case two-dimensional, and then you have all these totally disconnected points sitting far away, and then you have these things that are like hairy, except this hairy stuff might be higher dimensional hairs. That's why I didn't know how to draw it. So maybe think of some of these are two-dimensional hairs. Okay.
Why two-dimensional hairs?
Because for curves I was in dimension 1 and everything was one-dimensional. When I go up in dimension, like dimension 2, there's no reason that everything should stay dimensional. Already the skeleton, the core is two-dimensional. I can't insist that the things that connects into classical points is. And then in graphs, if you give me a classical point, there is a way to bring it down to the graph. If you give me a classical point on the curve, there is a retraction map to this. And here also there is a retraction map that can be written, and it's called tropicalization map. So this is a map from the classical points down to what we call the skeleton. Okay. 5 minutes. And let me just say very quickly, in hindsight, my electrical network problem that I was trying to solve, it turns out doing electrical networks on trees, on that contractible hairy part, is not interesting at all. It's trivial. If I put a battery on one side of the hair, the current is going to come directly to the graph. There's no branching that it can take. So I was focusing on that core of the Berkovich space, and I was really doing, in hindsight, potential theory on Riemann surfaces, non-Archimedean Riemann surfaces. Potential theory, I mean solving Laplacian equations and things like that, Poisson equations. And the torus that I attached to a graph was actually, so a curve has a Jacobian, this curve has a graph, this Jacobian has a real torus, and I was just working down here. So I was really doing Berkovich spaces in disguise, purely combinatorial. Okay? That's just a change of point of view. I could still prove all my theorems purely combinatorially anyway. I'm just saying you could interpret those theorems in this language. Okay, now the last 2 slides are going to be, I have to apologize for non-number theorists, which is a good number of you. But I just want to say that all these abstract nonsense, all these very concrete things, has an abstract nonsense application. So very quickly I'll say a couple of theorems. I want to finally deal with the abelian varieties, and I want to give you 2 theorems about abelian varieties. The first one, so I start with a G-dimensional abelian variety. I realize I shouldn't assume everybody knows what that is, but I hope you know elliptic curves. If you don't know, just think of solutions of this very particular equation. And it's a fantastic observation, I think, due to Euler, if I recall correctly, that the solutions of this equation actually forms a group law. So you can, if you have 2 solutions, you can add them. There's a way to add them and get a third solution. I'm going to assume A and B are rational numbers, and they're not unlucky rational numbers. Some relation between A and B is forbidden. Some third power of this, second power of this, plus third power of this, up to 4 and 27 are not zero. A smooth elliptic curve. So that's G equal to 1 example of the first item. These things have 2 numbers that capture the complexity. One of them is faulting height, so very difficult to define even for number theorists. I'm not going to do that, but just think of this as you have this object, and you want to know how complicated it is. And you can come up with some real numbers that capture this complexity. It's called faulting height because he used it in his proof of Mordell conjecture, which led to his Field's medal. So he wanted to show that there are finitely many abelian varieties of with some property, and he measured their complexity using this number. And there's another one which is called Néron-Tate height. And a while ago with Robin, we proved that these 2 numbers, people were wondering how these complexities are related, and we essentially show that these are up to some constants and stuff like that. They're essentially the same thing, except there will be these I invariants coming from different Berkovich spaces. So for any prime, you get a Berkovich space, and you can compute the I invariant of the skeleton of that Berkovich space. And we are saying that the difference between the two complexities is precisely captured by those combinatorial stuff I was saying earlier. And in fact, I was saying for Jacobians how to compute these things in terms of the electrical network of the graph. Right? I was saying how one can compute I invariants. That's one theorem. I don't want to dwell too much, but I'm happy to talk with experts afterwards. Again, for abelian varieties, there is a much more classical, actually, or more fundamental, or more basic notion of heights, which is called Néron-Tate height. Now you have an abelian variety like this. You look at the solution, a point in this abelian variety, and you want to know how complicated is that point. Point, not the abelian variety itself. So up to, in the previous slide, I was saying you have an object, what's the complexity of it? Now I'm saying, you give me this object, I'm going to compute the solution of it, and I want to know what's the complexity of that solution in that one example. This is a very important notion. So Falting's theorem has a second proof due to Vojta, Jackson's former postdoc mentor, which uses this function in a crucial way, ingenious way, and he also, there are new advancements for Falting's theorem using this function. Néron had a decomposition theorem for this, so for any place, he would say that this global number that you care about can be decomposed into smaller numbers that you should be able to understand better. Think of this like prime factorization. If you have a number, like my 8-year-old now is learning factorization, if you have a big number, you might want to know what are the ingredients of that number. What is the prime factorization? So these are the ingredients of that global number. And the last theorem I wanted to say is that using this point of view of tropicalization, we say exactly how to compute these numbers in terms of tropical geometry. So there is some intersection theoretic term, I, but maybe I should focus, my talk was focused on the second term. Namely, I'm saying, if you give me a point in the solution set, we should bring it down to the skeleton, tropicalize it, that's trop x, and then compute how complex this is using what I called f-trop, which is the very last part of my slide, is saying that this f-trop is essentially that closest lattice point function I was talking about, up to a shift and a constant. So this is a shift, this is some universal constant. It's just that weird norm of theta function that I was saying, find the closest lattice point. So this, in fancy terms, the local canonical height can be computed in terms of some intersectional Néron model, which is the first term, plus that very concrete quantization number. And I will skip the history of this and why this might be useful in application. And that's all I have to present. Thanks.